So we will be starting with the next topic, that is link state routing. So basically in the previous class we have seen like distance vector routing. So in distance vector routing, the basic idea was to find out like what is the distance between the two routers, okay, or the cost basically. So between different routers, what is the cost? Based on that, the routing is being done. Okay. In case of link state routing, here it is somewhat different from the previous one in some points. So basically, in the previous case, like distance vector routing, so whatever the cases were there, like different routers are there, so they were sharing their information. Okay, so they are sharing their information with the nearest or the neighbors routers only. Okay, and also it is like based on that sharing, it is going to update its distance basically. But in case of link state routing, what it is going to see is, it is each of the router will be sharing its initial table with not only the neighbors, it will be sharing with each of the router available to the network basically. So, and also in the link state routing, it will be having the knowledge of a particular link, uh, basically in terms of different parameters, like there is also uh, information that is called the sequence number. So in this link state routing table, suppose we are thinking in that way about the A is the router. So for A's table, it will be having two more information along with the destination. So like A, then C, D, or B, and E. And with respect that, what is the cost values, like for A it will be 0, for C it will be 2, for D it will be like 3, for B it is 5, and for E initially it will be infinite. Okay, so this will be there. Along with that, there is a sequence number, and also there is information that is TTL, that is time to live. So these are the two more informations added to the link state routing table basically. So here basically in link state routing table, initial will be like initial routing will be prepared with respect to each of the router. Okay, and first step here will be like initialization. In the previous one also we have seen like initialization. So each of the router will be preparing its own routing table, that will be called like link state routing table. It will be having the neighbors information, and for like this one is having no direct path with E initially, so it will be having infinite as the case. Okay, so this will be the initialization step. So after initialization, there will be the concept of flooding. So instead of sharing just with the neighbors, in case of a link state routing method, here each initial routing table of each of the router will be shared with all the routers available on the network. Okay, so suppose we are thinking about the A's only. So initially the A is having the table likewise. Okay, so after getting the path from, or after getting the table of each of the router, the final routing table that will be obtained at A will be having each information about each of the path going to each of the router. So it's like whatever is the routing table after the flooding in the sense here the sharing is done. So in the previous in the distance vector routing protocol we have seen like sharing was done. So sharing was done to the neighbors only. But here in case of link state routing protocol, the flooding will be taking place. So once the flooding is taking place means D will be sharing its table, initial table with A, C also sharing, B is also sharing, and also the E will be sharing. E will be sharing, so it will be reaching to A. So after getting each router's initial table, the A will be having the basic idea like what is the number of routers available into the network and what is the distance between each of it. So each of the router will be having knowledge of each of the node or each of the routers and its costs basically about a particular link. So this is the complete network. Initially this was the complete network, but after initialization and then after flooding, so after flooding the data of each initial routing table have been obtained by each of the router. So after getting the information, each of the router will be having information of every link and its cost. So that's why it is showing like at router A it has the information with respect to its routing table. It has the information of complete list of uh, routers and its weightage. Similarly, the D is also having the complete list of routers and its weightage of particular each of the link. Similarly, the C will be having the same, means the complete structure of the network with 5 different routers will be having this information to each of the router. So this is basically called like global knowledge. Global knowledge in the sense the routers, each of the router is having the knowledge about each of the routers that is available on the network. So this is called like a global knowledge. So each of the router will be having a global knowledge. So now once they have the global knowledge means they have this list or this network structure with each link, what is its cost. This information is available to each of the router now. So first step was like initialization, then flooding. So after flooding they will be updating its table and finally they will be knowing each and every link and its weightage, that will be considered like a global knowledge. And after this there will be fourth step will be like they need to use, they will be basically using the shortest distance between each of the routers. Okay, so suppose this is the source one, so from this source one it is going to D, C and B and then E. So what is the smallest distance, that will be find it out with the help of Dijkstra's algorithm. Okay, so now it will be use it will be using Dijkstra's algorithm to find out the shortest path or minimum distance, or will be calling like the shortest path. It will be finding out the shortest path. So this is the basic concept of the link state routing. So link state knowledge. So link state knowledge in the sense initially it will be having the knowledge about, so initially the age state links will be having like the knowledge of only 3, 2 and 5. So similarly initially they will be having the knowledge of initial one, but after flooding and then getting to know each of the status of each of the links, they will be knowing the information about the complete links and their costs. Okay, so we will be taking an example. Okay, and by that particular example we will be looking like how we can find out the cases or how we can find out the shortest path. Okay, so before that we will just see like what is Dijkstra's algorithm basically. So here it is going to say like start. So first we will be starting. So it will be set root to local node and move it to tentative list. So it is like we need to set one as the local node. So like there are uh, there are basically 5 different routers are there: A, B, C, D, and E. Okay, so from A, suppose we are moving from A to C, B, C, D, and E. So what is the shortest path from A to B, C, D, and E? We will be able to find out with this. So we need to first set a local node. So we will be setting like, suppose here A is the local node. Okay, so here A is the local node and move it to tentative list. So this is like the tentative list. Okay, so tentative list is initially empty, means what is the shortest path that is initially empty. Okay, so once this tentative list is empty, means whatever if all the paths have been finalized, then the list will be empty, then we will be stopping. Otherwise, suppose the list is not empty, means we need to find out the distance. We find out here, so from A to C, D, and B we are having 2, 3, and 5. From B, A to B, 5, 2, 3, and here infinite is the distance initially. So we need to just find out the shortest path in this case. Okay, so in this case the shortest one is 2. Okay, so this is the shortest one. So once whatever is the shortest one, we will be uh, fixing it. Okay, so fixing it in the sense, now it is the permanent, it will be moving into the permanent list. Okay, so now we will be considering, we are going from A to shortest path is 2, so A to C. So we are going from A to C, means C's distance between A to C is fixed. Okay, so now the same we need to find out. Okay, so that means the same we need to finalize each of the distances into its permanent list basically. So once whatever is the shortest distance, we need to find out, put it into permanent list. So similarly, initially the tentative list is empty if the all the routers B, C, D, E have been finalized, its permanent list is obtained, then it will be considered like a list is empty. No need to consider further. So it is not need to stop. Otherwise, if it is not optimized, means not finalized yet the shortest distance, we need to proceed further among nodes in the tentative list. So tentative list is this. This is like the tentative list. Among nodes in tentative list, move the one with shortest path to permanent list. So out of this was the shortest one, so it needs to be moved to like the permanent list. So we can call it like this is the permanent list. Okay, likewise add each unprocessed neighbors of the last moved nodes to tentative list if not already there. So if not already there, we need to move it. Okay, so once we will be moving, after moving we need to find out again the shortest path here. If neighbors in the if neighbor is in the tentative list with larger cumulative cost, replace it with the new one. So we need to find out the distance between the this is like the local to this one. Okay, so this is like source to destination we want to go. So whatever is the distance, minimum distance, we need to replace it with that value here. So here it is 5, 2, 3, and infinite right now. So out of that, whatever is the minimum distance, we need to put it here. Okay, so this is the algorithm that we will be following. So just we will be taking an example and then we will be proceeding. Okay, okay, so suppose this is the example. Basically we want to consider this as an example. We will be following the steps to find out the shortest path, okay, with the help of Dijkstra's algorithm. And also we will be considering like how the information is given to each of the routers, to each of the members basically here. Okay, So here it is starting like this is the root one, means root node is this one, like local one. So set root to A and move A to tentative list. So A will be moved to tentative list, move A to permanent list and add B, C, D to the tentative list. So B, C, D is moved to the tentative list. So the same is we have moved A to permanent list, B, C, D is considered as tentative list. Okay, so out of that, this is the distance or the cost. So 2 is the shortest one. So move C to the permanent list and add E to the tentative list. So initially I have added each of them initially. So it is considered like adding these three once, and then but this is the shortest, so it is moved to the permanent list, and then E is added. Then again here move D. So out of because this is move to permanent list C, out of that, like here 5 is the distance, here 3 is the distance, and 6 is the distance here. Okay, so in that case this is the minimum one, so D will be moved to the permanent list. So after D, so 5 is the shortest one among like 6 for E, 6 plus 2, that is 8 is the distance. So B will be like moved to the permanent list, and finally then the E will be moved to the permanent list and the tentative list is empty. So now the algorithm will stop. So this is the basic idea how we can find out. Okay, so we will be just going with the table. Yeah, so here the routing table for node A is given. So finally after one round, complete round, the complete uh, sharing of the data, they will be finding out like this is the node and this is the cost, and what is the next router through which they will be reaching here. So A is directly connected with B, C, D with having weightage or the cost like 5, 2, 3, that is the direct one, and for E it is having the 6 as the minimum cost, and it is reaching through the router C. So you can just see, so here to reach E it has two paths, from A to B then C, or A to C then E. So from reaching, or there are another path like from A to C then B and then E. So out of that, what is the minimum one we need to find out. So from A, B, E, there is 5 plus 3, 8. From A to E, there is 4 plus 2, that means 6 is the weightage. Okay, so 6 is the weightage, that is basically. So this is how basically it is obtained. So we will be taking the same example and uh, see like how it basically works. Okay, so suppose this is A, B, okay, so this is the basic structure. Okay, so how we need to find out. So initially what we will be doing is, so suppose initially we are considering the D. So the first step is initialization. So we need to find out the table, the link state routing table for D. So it will be having D's table. So it will be having the sequence number and TLL. So TTL we will not be considering that. We will taking like from D to D we want to go, then suppose A, then C, and then B and E we want to go, and we need to find out the cost. So initialization will be done. The step 1 will be like D, from D to D it is 0, from D to A 3 is the weightage, from D to C there is no path, direct path, so it will be infinity, from D to B this is infinity, from infinity is showing like infinity is the distance, means there is no direct path right now at the initial stage. So between D to E there is no direct path, so it will be infinite. So this was the initial table that is formed. So similarly, if initial, suppose we want to find out for the B, so it will be B, suppose A, C, D, E. So B to B is 0, B to A is the distance is 5, B to C is 4 direct, path is there. B to D, there is no direct path, so infinity. B to E is 3. Yeah. So similarly, each of the routers will be having its initial table. If one will be there, and then it will be flooding. So flooding in the sense, each will be sharing its table with each other. Okay. So it will be shared to each other, and finally, once it is shared, they will be having the knowledge. So once the suppose a particular D is the one, it is receiving the tables from each of the node. Okay, so after receiving this D, or each of the particular router will be knowing like this D, it will be knowing like this D is directly connected to A with a distance 3. Then it will be knowing like after A it is connected with C with the weightage 2. Then D will be knowing like A is also connected with B with weightage 5. Then it will be knowing like C is connected with E with weightage 4. B is connected with E with weightage 3, and C is connected with B which is 4. So this is the information at each of the routers now after sharing, after the global knowledge. So D is also having the global knowledge, each router is having the global knowledge, so it will be able to know each of the link and its routers and their weightage. Okay, so this is the basic idea. So this is up to like they have the global knowledge of each of the routers and the links and its calls. Then it will be using the Dijkstra's algorithm to basically find out the shortest distance. So how it will be finding out, we will just getting it out. So suppose we want to find out for A. Okay, that means from A we are going to B, C, D, E, or you can take any value here or any node, we can take it. Suppose we are taking the E, means from E we want to go to each of the node. So A, B, C and D. So from E to A there is no direct path, so it will be infinity. From E to B there is a direct path 3. From E to C there is a direct path 4. From E to D there is no direct path. Okay, so out of that now we will be considering the smallest one. So this is the smallest one out of this. So now we will be making it into the permanent list. So after E we need to go to B for the smallest distance. Okay, so now from E to B we have reached. Okay, so from B can we go to A? Yes, we can go with the weightage of 5. That means if you want to go from B to A, it is taking 5, and from E to B it is 3. So 3 plus 5, that is 8. So 8 is less than the infinity. So here the weightage now will be like the 8. Okay, next this is already fixed, so it will be the same. Next one is like from E to B, can we reach from B to C? Yes, we can reach B to C, but it is taking 4 again. So it is 3 plus 4 is 7. So 7 is greater than this 4. So we will be retaining this 4 again, because we need to find out the smallest one. So it is 4 again. Then this D, can we reach from B to D? No, there is no direct path from B to D. So it will be again infinity. Okay, so now among this one is the smallest one, so we will be considering now E, B and then C. So E, B and C. So once we have considered E, B and C, E, B and C, so from C can we go to A? yes, we can go to A. So from C to A it is 2. Okay, so we need to find out this path basically. So here it is like E to B is 3, then 4 7 and 2 9. So 9 is the weightage. Okay, but already from E to B, if we want to reach from E to A via B, then it is taking 8 is as the weightage. So but this is going to take 9, so we will be retaining 8 only, because what is the minimum. Okay, so this one is already optimized and 4 is already optimized. Then we need to search for D. So from C also we can't directly go to T. So there is no direct path, so we will be taking the infinity. Next is we need to find out of here. So 8 is the smallest one. So we need to consider E, then B, then C, then A. Now we need to consider from E to B, B to C, or C to A. Or we can consider like from E to A. From E to A we have 8 as the weightage. From E to A, yeah. Okay, one mistake that we have done here initially. Okay, so okay, so once we have considered E to C, so we have reached E to C with a value 4. Then from E to from C to A, if we are going, so it is taking like 4 plus 2 is the weightage, 6 is the only weightage, but here 8 was given. Okay, so will not be considering 8 only, we need to consider here the minimum one. So from going from E to A via C, we can have a weightage of only 6. So we will be having a weightage of 6 only. So we need to put here 6. Okay. So now out of this was the minimum. So A we have taken. So from E to A via C we can reach, and it can have a weightage of 6. So now from A we can go to D. So this have already been optimized. So for D we need to consider. So from A we can reach to D. So from reaching E to A we are having a weightage of 6, and then from A to D we are having the weightage of 3. So 6 plus 3, that is 9. So with 9 weightage we can reach, or we can consider like suppose other paths are also there. So from E to B, A, and then D. So 5 plus 3 is 8, and then 8 3 11 is the weightage. But by this, by C, A, D we are able to reach by 9 is the only weightage. So okay, so 6 is the optimized one, 3 is the optimized one, 4 is the optimized one, and here the 9 will be the one. So now this is the minimum, so it is also optimized. So it is E, B, C, A, and D, and these are all optimized one. So now the here the list is empty, tentative list is empty now. So we will be stopping. So this is how from going from E to B we are having 3 as the weightage. From E to C we are having 4 weightage. From E to A we are having 6 as the weightage, minimum distance it is finding out. From E to D we are having the minimum distance of 9. So this is how the basic link state routing is basically done. So in the next topic, that is address mapping, we will be looking like how we can do the address mapping. So there are basically different methods to do the address mapping. So we will be looking few of it in this lecture basically. So here is like whenever we are sending a packet, we need to send only when we are having a specific connection, and to establish a connection we should be having the logical address and the physical address. like the MAC address. Okay, so the IP address is basically dealing with the network layer, and the physical address that deals with the data link layer. Okay, so whenever we are having the delivery of a packet, so delivery of a packet to the host or a router requires two level of addressing. One is the logical addressing, another one is the physical addressing. Okay, so logical addressing is basically the IP address, physical addressing is basically the MAC address basically. So that we have already seen. Okay, so we need to be able to map a logical address to its corresponding physical address and vice versa. So like if device or if a system is there into the network, it will be having an IP address and also a MAC address. So how we can map basically an IP address with its MAC address, that is physical address, or from a physical address to its MAC address. uh, we should be there, we should be doing, we should be able to do it. Once we will be able to do it, then we will be able to send the complete packet. Okay, so this can be done by using either static or dynamic mapping. Okay, so we will be looking like how the mapping can be done. So mapping from logical to physical address is done by using the ARP, that is address resolution protocol. This is address resolution protocol. And from physical to logical address mapping is done by using RARP, that is reverse address resolution protocol. So means from logical address, in the sense we know the IP address of a host or IP address of a device basically, or a host or a router. Okay, then we want to find out the physical address. So that is basically done by using ARP. Its reverse is, if we have the physical address, can we find out the logical address or IP address? That is done by using the RARP. So we will be looking at like what is ARP and what is RARP protocol. Okay, so in ARP protocol, basically there are two different operations. So one is called like ARP request, another one is called like ARP reply. So this ARP request is like, suppose a system is there, system A is there. System A is knowing the IP address of system B. Okay, so it is knowing the IP address of system B, but the system A does not have any information about the physical address, means the MAC address of the B. So before sending the complete packet to system B, we need to find out, or the system A needs to find out its MAC address also. So in that case, it will be sending an ARP request. It will be sending an ARP request that will be of broadcast type, means it will be going to each of the hosts that are connected to this network basically, or to this system basically. Okay, so it is sending a request. This request will be going to each of the hosts on this network, and because it is sending the request such that it is having the IP address, so the system that is having the IP address matching with the request sent IP address, that system or that host will only be accepting that packet, otherwise other hosts will be rejecting it. Okay, or discarding it basically. They will be discarding because there is no IP address match. So once it has received it, then it will be replying it. So this system B will be replying, so replying to the system A directly in the form of an unicast, means because system B knows like this request has come from system A, so it will be directly replying to system A with an unicast message format. Okay, it will directly going to the system A only. So here this request is like looking for the physical address of node with IP address this. So this is the IP address of this system, system B. Okay, so IP address is known by, already known by the system A, so it is sending like this is the IP address and I want the physical address of this IP address. So this is the request is sent, and in the reply the node physical address is this. So this is system B is replying to A like this is the physical address of node B. So this is the basic idea about the operation of ARP. Here the ARP packet is given. So how its packet is basically defined. Okay, so its packet is having different components like we have already seen the header formats. Okay, so here this is the first is like the 16-bit. First 16-bit will be considering the hardware type. So what is the type of hardware? So here what it defines basically, so defining the type of network on which the ARP is running. So what type of network it is running, okay, like whether it is Ethernet type. So if it is Ethernet type, in that different categories are there, what type of hardware it is basically utilizing, category 1, category 2, likewise. So this hardware type is being indicated by a 16-bit information. It will be indicating like what type of network on which the ARP is going to be running. Okay, next one is protocol type. So the value of this field for the IPv4 protocol is 0800 in hexadecimal basically. So if an IPv4 protocol is being used, so here this protocol type will indicate like what protocol is being used for the communication or the data transfer basically. So what type of protocol is being used? So if it is IPv4, in that case it will be having the value like 0800 in the 16-bit format. Next is the hardware length. So hardware length in the sense, so whatever is the hardware length, it defines the length of the physical addressing in bytes. So physical addressing in the sense, so whatever is the source physical addressing and destination physical addressing is there. So physical addressing, whatever is the physical addressing in the sense the MAC addressing. So what is the MAC addressing size basically? So are the physical addressing size. So in that case, if it is like a MAC address, it is talking about the MAC address. In that case, it will MAC address is defined by like 6 byte. Okay, so here hardware length will be in bytes, that will be in 6. So if it is there, it will be a 6 byte Ethernet address basically. Okay, so that will be the physical address in byte. What is the length of physical address in bytes? Next one is protocol length. So protocol length is it is talking about the length of the logical address. So this is going to define the physical address, this one, and the protocol length means the, because IP addressing it is talking about. So if it is IP addressing, it's of 32-bit means 4 byte. Okay, so protocol length, if it is using IPv4, it will be talking about the logical addressing, that is of 4 byte. Okay, so here it will be having 4, here it will be having 6 because it is MAC address. Next 16 bits will be indicating what type of operation it is. So if it is, its value is 1, in the sense it is talking about a request, means it is a ARP request packet. If its value is 2, means it is a reply packet. So it defines the type of packet that is being sent. Next 32 bits will be the sender hardware address. So sender hardware and address in the sense, so whenever it is sending, it will be sending the IP address of the sender, physical address of the sender, and then IP address of the receiver. And in case of like the physical address, it will be sending 00. Okay, so this is the basic idea in case of while sending it, while the request is being sent. So here the sender hardware address will be required. So 32-bit representation. Okay, or if it is hardware address in the sense physical address, it is talking about physical address in the sense like it is a MAC address. So it is variable in length. Okay, so it is a 6 byte, it can be a 6 byte in case of an Ethernet. If it is an Ethernet type of connection, then it will be having the 6 byte of address. So sender protocol address means sender IP address it is talking about. So that will be of 4 byte of information for IP addressing. and the target hardware address. So here it is not filled in a request. So in a request packet, this value is basically the 0000. It's all the 6 byte values will be 0, and target IP address will be of 4 bytes, similar to the IP address of the sender. This is the format of ARP packet and different fields that are defining different functions. Yeah, so that will be starting from the network layer, then it will be going to the data link layer. So once it is packet, it is going to the data link layer. So from the network layer, this is the packet, it is going to the data link layer. So in data link layer, it is going to be encapsulation, it's going to take place. So this will be part of the data, and along with the data there will be some different uh, headers and uh, preamble and SFD start frame delimiter, and these are the data that we have already seen, like what is preamble and what is SFD, along with that destination and then source and what is the type basically. So these are the information that are being added into the frames. Okay, so encapsulation will be doing, so whatever the data coming from the network layer, it will be encapsulated along with the headers and the trailer bits. Okay, so these are the steps involved in ARP process. So what is the complete process? These are the different steps given. So first is like the sender knows the IP address of the target. So initially the sender knows the IP address of the target. There are different ways through that it can find out the target IP address. IP asks ARP to create an ARP request message. So internet protocol, this IP will be asking ARP to create a ARP request, filling in the sender physical address, sender IP address, and the target IP address. So these are the three informations that will be filled into this ARP packet. Okay, so this is 1, 2, and 3, and this is unknown. This is unknown, so it will be filled like 000 32 bits 000. The message is passed to the data link layer where it is encapsulated. So this ARP packet is passed to the data link layer. This is at data link layer. It will be encapsulated in a frame by using physical address of the sender as the source address. So here at the source address will be the physical address of the sender. So here the physical address of the sender as the source address and the physical broadcast address as the destination. So physical broadcast address will be like 0000. So 00000 will be the destination one. So it will be the broadcast address for the destination. So every host or routers receive the frame because it is a broadcast address. Every hosts and routers will be receiving the frame. Because the frame contains a broadcast destination address, all stations remove the message and pass it to ARP. So it will be going to the ARP. All machines except one targeted drop the packet. The target machine recognized its IP address. So means the broadcast message will be reaching to each of the hosts and routers. They will be decapsulating the frame. After that, they will be matching. Okay, so matching its IP address. If it is matching, it will be accepted, otherwise they will be dropping it. So the target machine replies with the ARP reply. So it will be replying the message that contains the physical address. The message is unicast. It will be only intended for the sender only. So the sender receives the reply message. It now knows the physical address of the target machine. So once it knows the physical address of the target machine, now the IP datagram or the IP packets which carries data for the target machine is now encapsulated in the frames and is unicast to the destination. So instead of broadcasting, if they don't know the address, it's not like whatever is the original data they will be broadcasting to everyone, but once they have established the connection by you knowing the physical address of the destination, then they will be unicasting directly to that particular destination. So this is the basic idea of ARP uh, uh, routing protocol basically. Here are the 4 different cases of the ARP. It's like if a host to host data needs to be sent, means into the same network, into the same LAN, 2 different hosts are there. So one is the sender, other one is receiver. So in that case, whatever is the target IP address, that will be the destination address in case of IP datagram. So here a host has a packet to send to another host on the same network. So this, in that case also the ARP can be used. The next case is case 2. Here a host want to send a packet to another host on another network. Okay, so this is the sender, but the receiver is connected to another LAN, so LAN 2, and here is the receiver basically. So this is the receiver, it is connected to another network. So this is network 1, LAN 2. So in that case also the ARP can be used. So in that case, the packet that will be sent, or the ARP packet that will be sent by the sender, it will be sent to the router. Okay, so router will be having like a destination. So with respect to the router, it will be sending to router, then now router will be sending to the receiver likewise. The second case, the third case is like here the router to router. So it's not like only one router is there. Suppose there are another router, so it will be sending the sender will be sending to the router. So this router will be sending to the another router, router 2. Then this router will be sending to the receiver or the destination. So likewise. And here the fourth case, a router is sending to the receiver. So the same thing is given, like it could be like within the same network or within a different network. If there is it is within a different network, this case 3 and case 4 will be playing the role once the receiver or the destination is in the another network. So some points are there. So an ARP request is broadcast type, and an ARP reply is a unicast. So we have already seen. So here is an example given. So in that case, the example is like a host with IP address this and a physical address this has a packet to send to another host with IP address this one and a physical address this one. The two hosts are on the same network or the same Ethernet network, so both hosts are on the same network. So the ARP request and reply packets encapsulated in the Ethernet format. So what will be the ARP request and reply packets, and what different components will be having, and the values it is being asked. So these are the two hosts basically. Okay, so here this is the figure that is basically going to consider the ARP request. So this is the ARP request and this is the ARP reply basically. So this was like the IP address of the sender, and this is the physical address or the MAC address basically. This is the IP address and this is the MAC address of the receiver basically. So once it is going to send the request, so here the first part that will be basically the so this is the ARP packet. Okay, so the first part is going to be the hardware type. So what is the hardware type? So if it is a Ethernet type of hardware, it will be like its value will be 1. Okay, so here its value will be 1 if it is an Ethernet type, and this is 0800. This is when the protocol type, it indicate the protocol type. So if it is IPv4, so it will be 0800 will be the value, its value will be there. Next one is the physical length. So the physical length is going to indicate like what is the physical uh, address or the hardware address basically, what is the length of hardware that is. So here it is like in MAC address we are talking about. So if it is MAC address, it is like 6 different bytes are there. Okay, so its address is basically given by the 6 different bytes. Okay, so and it is like byte 1, 2, 3, 4, 5 and 6. So MAC address is defined by 6 byte, so this is given by 6. And next one is the protocol length it is talking about. So this is basically the IP address length. So IP address is like byte 1, byte 2, byte 3, byte 4. So 4 byte is there, so here its value is 4. Next one is 0001 is there. So this 1 indicates it is a request type. Request in the sense ARP request is this value indicate, and this will be the MAC address or the physical address of the source or the sender. Here, so B2334, this will be the value of the MAC address, that is of 6 byte. Next one is the sender IP address. So it is 130.23.43.20 sender IP address. In the destination or in the destination hardware address, here basically 000 is there. So 32-bit 000 value will be there, that will be considered as a broadcast message. This is the broadcast message, it indicates the broadcast message. And next one is the IP address of the destination, this is there. So this is the request packet, request ARP packet. Once it is received by the receiver, it will be replying with an ARP reply. So in the ARP reply, again everything will be same, the different will be like the operation type. So operation type here will be the 2, that is the reply. So it is a reply, and then once it is replying, the source, now the source will be the source physical address will be the physical address or the MAC address of the B, okay, and the IP address will be now here the IP address of B. And similarly it knows the physical address of the A, so it will be putting the physical address of A as the destination one, and destination IP address will be the IP address of the A. So this packet will be sent as a reply. So this is how it basically works, this IP request and IP reply basically. Okay, one more point is like the proxy ARP. So here proxy ARP is a technique called proxy ARP that is used to create subnetting effect. So subnetting effect in the sense, so suppose there is a router or a host, it wants to send a request, so it will be sending a request to whatever is in there, so it will be like a broadcast message. So if it is connected with the proxy router, okay, so it will be going to the different hosts, along with that it will be going to the router also. But here this router will be behaving like, if it is a proxy ARP router, that means instead of this host with having IP address this and this, there instead of providing their physical address, this router will be behaving as the physical device on behalf of these devices or these hosts basically. So here on behalf of these hosts, this proxy ARP will be behaving as its own, okay. So here what is its meaning? So a proxy ARP is an ARP techniques ARP that acts on behalf of set of hosts. So it will be behaving based on some set of hosts. So these hosts will not be replying on behalf of these hosts. This router, that is proxy ARP router is there. So this proxy ARP router will be behaving or replying on behalf of these hosts. So whenever a router running a proxy ARP receives an ARP request looking for an IP address of one of these hosts, IP address of one of these, the router sends ARP reply announcing its own hardware or the physical address. So instead of sending the physical address of these hosts, this proxy ARP will be sending the physical address of its own as the physical address of these devices. So on behalf of these hosts, this proxy ARP will be behaving. So this is the basic idea of proxy ARP. So after the router receives the actual IP packet, it sends the packet to the appropriate host or the router. So after the router receives the actual packet, so once it will be sending its reply. So reply will be sent by this only. So here this is the reply is received here. So after reply received, this router will be directly sending data to this proxy ARP router, and then this router will be sending to a particular IP address. So this is the basic idea of proxy ARP routers. Okay, so the next point we will be looking at like RARP. So RARP, that is basically opposite to the ARP protocol. So RARP is basically not used nowadays. Nowadays some different techniques are there that are basically used, like boot P is there that will be used, but we will just see like what is RARP. So here it is going to do the mapping from physical to the logical address. So it is opposite to the ARP. So ARP is going to map from logical address to the physical address. But here the sender knows the physical address of the destination, but not knowing the logical address. So in that case, RARP will be used. So we will see like where is the cases like these RARP can be used. So RARP can be used when the physical address is not known. So physical address is not known means, so how the physical address cannot be known, or what are the cases basically. So there are occasions in which host knows its physical address but needs to know its logical address. So this may happens in two different cases. The following cases are given. So like if a particular host is there, it knows its physical address, but it have no information about its logical address or IP address. So here the example is like diskless station is just booted. If any station is there without any disk is booted, just booted, so the station can find its physical address by checking the interface like NIC network interface card, but it does not know its IP address. If this diskless station is just booted, in that case its IP address is not available, but it can obtain its physical address from the NIC card. Or another case is like here an organization is there that does not have enough IP addresses to assign to each of the station. In that case, it needs to assign IP addresses on demand. So if there is no enough in IP addresses available to a particular organization, then it will not be assigning the IP address directly. It will be assigning based on the demand. So in that case, the physical address is known, but the IP address is not available. So station can send its physical address and ask for a short time lease. Okay, so then it will be sending its logical address likewise. So here to know the physical to know the IP address, once the physical address is known, the reverse address deletion protocol RARP is basically used. So it finds the logical address of a machine that knows only its physical address. Okay, so here the IP address of a machine is usually a read from its configuration files stored on a disk file. So we can find out the IP configuration files from the disk files. Okay, but however diskless machine is usually booted from ROM, which has minimum booting information. So because diskless machines are there, they directly boot from the ROM, but in the ROM they basically store minimum information, so they don't have the information about the configuration files. Okay, so that's why there is a lack of logical address without having with having the physical address. They don't know the logical address basically. So the ROM is installed by the manufacturer and cannot include the IP address because the IP addresses on a network are assigned by the network administrator basically. So that's why the ROM could not be having the IP addresses. So that's why only the physical address is known to that systems. Okay, so here the machine can get its physical address by reading its NIC card. Okay, which is unique locally. It is already known to you. It can then use the physical address to get the logical address by using RARP protocol. So by using RARP protocol, you can get the logical address. So the steps that are there to obtain the logical address is here, and RARP request is created and broadcast on the local network. So step 1 will be like this. It will be broadcast to local network. Another machine on the local network that knows all the IP addresses will respond with the RARP reply. So there will be an RARP request, that will be a broadcast type, and then the machine that is knowing the IP addresses of all other devices, they will be responding as an RARP reply. The requesting machine must be running an RARP client program, okay, and the corresponding machine must be running the RARP server program. So here the requesting machine should be running in RARP client mode, and the one that is replying, it should be running in RARP server mode. Okay. So there is a serious problem with RARP, that is like broadcasting is done at the data link layer. Okay, and the physical broadcast address, that is in case of Ethernet, does not pass boundaries of a network basically. So in the case like this is the case, like broadcasting is done at the data link layer. Okay, so but the physical broadcast is not going to pass or not going to enter into the network layer. So that is the basic difference between RARP in case of resoluting the internet, the IP address, basically internet protocol address. So the basic problem with respect to RARP is the link between the data link layer and the network layer while decoding the logical address basically. So this means that if an administrator has several networks or several subnets, it needs to assign RARP server for each network or subnet. So that means, because from data link, from going to the network side, it is like a network is administrator is there, it is having different networks and different sub networks. So whenever there is a packet coming, okay, so once it is going to the network side, okay, so it should be assigning a separate network for each of the RARP's packet. Okay, so this is the costly thing in case of RARP. So this is the reason RARP is almost obsolete. So RARP is not basically used. So the two different techniques that are basically used is BOOTP and DSCP is the one that is basically going to replace the RARP basically. Okay, so this is the RARP and the ARP protocols. So next we will be looking at ICMP and IGMP protocols in the next classes. Okay.